Okay, with that, the base, let us start. So, for others, have you heard about liquid marbles? Not in the program schedule? Yes. What is liquid marble? Liquid encapsulated by particle. Good. Have you seen it before? Not in the lab. Not in the lab. Yes. Good. Honeydews. Honeydews. Perfect. Very good. And when you observe, the first rain, because you have powders, right? On the soil, right? Only it happens in the first rain. Okay? In the first rain, nature produces liquid marbles. Okay? So you don't need any laboratory, all these things. Okay, so the point I want to tell is like, the nature use it as a tool, right? So that means it is important. The thing is, soils have different character. You take sand, okay, and these are porous, okay. So if you do immediately, it will form liquid marbles and it will collapse, okay. So you cannot see liquid marbles sustaining marbles. It will form. Then, since it is porous, the liquid will try to enter to this, the particles, and it will. Okay, so let us start. Yeah, anyway, today we are all introducing ourselves, right? So Damien also did, so I will do that. So I completed my PhD from Technical University of Darmstadt, Germany in 2013. Then I joined with him. Okay. So now after 10 years, we are rejoining. So, okay, so today basically we are going to discuss mainly about, it's the right time to discuss because it's all raining, right? It's beautiful. Yesterday's lecture also we were able to connect to nature. Today also, tomorrow also I will come back with the wettability and all on some other kind of surfaces. Okay, that's what I told. I will not go to the things which we cannot see. Damien will do that. Okay, so let us start. What is my starting point? Yes, this is my starting point. So yesterday we all have seen the lotus leaf and all. The Kerala is really beautiful in Kerala. So one side you have the Vayanadu starting point of rivers, the other side beach, on top you have clouds, the rainy, all the things, and bottom we carry umbrellas. Okay, so somehow the spectrum is covered. And on the right hand side on bottom is like, this water is not such friendly, right? He can be really problematic at situations, right? So it's like the landslide happened in 2000, last year, September, right? August or September in Vayanadu, which killed like, hundreds of people. So it's like a very powerful, but we are actually, luckily in the lab, we are actually playing with the droplets. So harmless, hopefully. Okay. So today we are actually going to discuss about the impact dynamics, not as the physics of impact dynamics, but in the point of how we can connect it to liquid marbles. Okay? So if a droplet impact on a surface, depending on its energy, also depending on the properties of the surface, right? Yesterday we discussed like the wettability and all is all about the interactions, right? How the surface tension of the liquid matters, surface energy of the surface matters, roughness matters, how much energy it carries matters, right? And accordingly, he will take a decision what to do. Okay? So you can see different regimes you can identify. It can be simple rebounds or splashing, right? You can see identify different variants, right? The droplet impacting on surfaces. There was a video that we removed, right? Yeah, before starting, we should have some motivation, right? So, what you are seeing is, they are not droplets, they are liquid marbles actually. Okay, I would say this. Okay, so you can see like, two oil droplets, okay, on water. on water surface, and they come and merge together, right? How? They don't know each other. How? They are well separated. You take the dimension of them. Well separated, right? 10 times, 20 times far away, right? And they don't have eyes. They are not emitting anything, at least in our knowledge. But they do interact, right? And they merge. Why? This is not connected to liquid marbles, but it will be a part of the upcoming talks. Okay, so it's capillary interactions. Have you heard about Cheerios effect? Cheerios effect. It's basically, yesterday some group did similar experiments, right? Deform the surface and see how the droplets moves. So they somehow generate an attractive force. Here the point is like, okay, if it is immiscible, oil, or if it's completely solid, because the water surface is one of the platform we want to do reactions. We do reactions, right? Not always on solids, right? But as Damien rightly pointed out, because that's the connectivity, right? Functionalizing surface. Yesterday we discussed about manipulating the contact angle gradient, right? Making contact angle gradient using temperature and all on a surface, right? It was relatively easy, right? But Damien today told surface, water surface, liquid surface is more problematic, right? Because the point is like, if you try to disturb a small portion of water, it can somehow reconfigure, right? Either through inducing a flow or by adjusting the shape. It is more flexible to adapt to the situation. So that is why, the functionalizing you can do with the surfactants, particles and all. That's what we are going to discuss. The point here is, can we transport water over water? Applications do require that, right? Suppose you are thinking about you want to perform a specific reaction at a specific point. Or a droplet having this much lifetime should sit on a water surface, we can say, right? Some examples I am saying. But can you directly put a water droplet on a water surface? It's not possible, right? Basically, he will simply merge with the other part, right? So the question is, can we transport water over water? Okay, it's not possible in the exact shape of water, right? But preserving its properties and allowing it to somehow interact with the surroundings, can we do it? The answer is the liquid marbles. Okay? I hope the landing is clear. This slide I will skip. This also I will skip. Yeah. So let us see the difference between a droplet and a liquid marble. You can see a droplet placed on a surface, right? It acquires a contact angle, right? By sensing, depending on its surface tension and the wettability of the substrate. We have a detailed discussion yesterday, right? How these shapes forms. And it comes with that hysteresis, right? Yesterday we discussed a lot, like, how we can mitigate with the hysteresis. What are the alternates? So here the point is, can we make a non-sticking, it's a sticking water droplet, can we make a non-sticking water droplet? That is actually the concept of liquid marbles. Okay? David Curie is also from Paris. He is the person who really appreciate this concept. So a lot of applications, we will not simply say the applications at the moment. Let us see how it works and what are the ways we can make it. Okay? Yeah, so let us see. You take a water droplet over a water surface. You put particles, right? You have to put particles, okay? Then what happens? If the particle is completely hydrophilic, super hydrophilic, the first one you see, he will not stay at the interface, right? Because it's a completely wetting scenario, right? That means he will, see, he somehow loves water. So when he sees, because he is coming from air, okay? But he is philic to water, okay? So then when he comes to the phase boundary, liquid air interface, he always tries to go to the water phase, right? So that he will not stay stick to the interface. On the extreme other side, if it is completely phobic, we have seen the properties of superhydrophobic coatings yesterday, right? You can think about the reverse, right? Yesterday we discussed about the hydrophobic coating and the normal liquid. You can put the other way also, right? Particles can be superhydrophobic and then you put the liquid. He will not stick at the surface, right? He will not get adsorbed at the surface, right? Because there is no need, right? And another point is water is also not so happy, right? Because he is phobic. And if he is trying to adsorb, his energy level is not going to affect, right? Because, when something happens, we will do something if you will get calm, right? That is the point in the nature, right? We will not do any work if you are getting, more tense, right? So trying to reduce the energy of the system is the whole principle of, all these kind of reactions and all, okay? So what happens in the intermediate state? In the intermediate state, the situation is very much interesting, right? Around 90 degrees. So 90 to 120, 110 degrees. It will make a kind of, the meniscus and would try to stay at the interface, right? Okay, the density of the particles matters, but we are not worried too much because they are too small that gravity is having no significant impact, okay? They can adsorb at the interface, okay? And they can reduce the interfacial energy based on that expression, okay? That's fine, where R is the radius, gamma is actually the surface tension of the liquid. You can find out, okay? Then the question is, okay, particles get adsorbed. There's actually a droplet transformed into a liquid marble, right? Then the question is like, when you shake, why they are not going out? That's a good question, right? Because when something is getting adsorbed here, when I shake, yesterday some of you have done the experiment, it's not happening, right? Somebody carried the liquid marble from second floor to the ground floor and did the evaporation and still particles were there, right? And the liquid has to go out, right? Particle is not going away, right? That's what happened, right? Yes. So they are so stable, right? What could be the reason? I will not tell the answer. That's a homework, how to think and that, okay? If I shake the marble, still, now if it is not stably attached, it will throw away, right? It's not happening, it's so strongly adsorbed. What could be the reason? If you have to think. Maybe it's a potential question for your evaluation. Okay? You have to think. Okay, so now the second part, okay? This is a schematic, it works fine, a beautiful schematics, a monolayer of particle, it never happens like that. Okay? I'm not saying never happens like that, once in a while it can happen. But monolayer is always, you can have particle aggregates, the situation is more complex. Multi-layers, everything is fine. With all the errors happening in this nature, we are still getting liquid marble. That is good enough for us. Okay? So, the point, yesterday somebody asked me, I tried to recall the face. That okay? I don't know. My brain is so bad. So, we are actually putting a droplet, rolling. I think you asked me, right? Yes. Is there any repeatability? This was your question, right? It's a poor approach. That was the, Repeatability is there because everybody got liquid marbles, right? So liquid marbles are forming. So whether they are identical, there is a question, okay? Because I told you, like, we are having a particle bed, putting, maybe some aggregates, how you put may be different, how much times you roll can be having the jamming factor, jamming effect. Okay, so they are liquid marbles, but we see like, if you have a protocol 10 times you roll, statistically we get a decent performance, okay? But still that is not the, the perfect way to make liquid marble, that's what we feel, or my team, previous member Lakshmi as well as Ardra also have the same feel, okay? So then we are more interested about next level of marbles. It's called the Janus liquid marbles. Okay? What is actually the concept of Janus? Is a goddess, right? Having a dual face, right? So the point is like, it's actually a marble having dual properties. One side it can have one particles, the other side it can have other particles. It can be, I'm saying particle, it can be chemically different, physically different, particle size, anything. Because that's very important, right? Suppose you think about an application. Okay, you want to keep the marble on a surface in a specific orientation. That means, you can program or you can function, because when we listen Damien's talk more and more, we will use the word program more and more. Okay, so functionalize one side, you can have a preferential adsorption, right? Which is not possible with a normal liquid drop, right? Even with the pristine liquid marble, it is not possible, right? So that is why we go for a higher level advanced marbles where two or more particles. These Janus marbles are two particles. Okay? So we can see the concept, the basic approach people do is, okay, they make one white marble, one black marble. Now, you know how to make it, right? Do it like this. Do 100 times. If you are lucky, 10 times you get the Janus marble. Because you are actually, you see the complexity in the physics, what is happening when you try to push it. The way we do is looks very simple, but if you take a high-speed video of that process, it's very complicated, right? Basically, when you press two marbles, what happens? So you have your first marble with the particles. I remember Damien also drawn something, mentioned kissing and all, right? Some figure, something identical. But at a very small scale, he's saying, I'm saying about a large scale. So when you put them together, this is what the first figure says, right? I have a white marble, I have a black marble, and these particles are there, right? And when you put, to have a successful liquid marble, Janus liquid marble, the water should get connected by displacing this particle, and this particle should rearrange, right? Because it is in a completely curved state to a semi-state, right? But for liquid, there are many other ways to escape, right? Why liquid always escape in this way? Because you are applying a pressure. If there is a small defect here, gone. Because I told you, it is not always a perfectly coated marble. There can be aggregates, there can be defects, right? So this approach, even though conceptually it works in the Bermishango did it very nicely, we appreciate everything. But practically, repeatability is a question. Okay? Yeah. Let us see how such marbles looks like. Okay, if you make a mix, put a droplet, what kind you will get? You will get a mixed marble. You are not like getting you don't have two faces. You have maybe having skin color mixed, which will not do the purpose, right? Because still it is isotropic, right? Because if you take the statistics, it is isotropic, right? I need a complete anisotropy, right? One side is completely different, right? So that won't serve the. People do these kind of things to make it like a more magnetic, like, if you add some magnetic particles, you can pull it. But it will not give you Janus liquid marble. I hope it's clear, okay? So the point is, and this is a slow process. You have to make two parents and make a baby out of it. Baby is much larger than your parents, right? So these are problematic because, when you go scale down to smaller and smaller droplet, they are much more stable, right? So then when you push, this process gets more and more problematic. So the approach is like, can you propose some new approach? Then in ACS Applied Materials Interface in 2013, I don't have an image here, they did a clever approach, okay? they made something set up like this. Okay, so they will have a one type of marble here, other type of marble here. By adjusting the height, you can control the potential energy, right? So they somehow, allow them to merge it to make Janus liquid marble. Here also, the concept remains the same, right? Instead of you do this process, you do this process. That's all, right? I can continue, right? Yeah. So the point is like this is also a slow process, whatever the issues we told sustains. So the point is, my previous student, Lakshmi, we were thinking, okay, we didn't start to, in science we never do like that, right? In the end we say like, we did it in that way, but we were exploring some other impact dynamics, and we identified a very beautiful flow field upon droplet impact. So that inspired us to reach to very interesting couple of second thesis is going on, patent is there, and we are looking forward. So let us start with that. So the background is clear, right? Liquid marbles are very important species like droplets, okay? Because the important is like, they are porous. That means they can sense to the environment. Even though they are solid, they are still porous. That means you can use it for controlled chemical reactions, drug delivery, a lot of things. You can make medicine, Ayurvedic medicine, edible oil, edible particles, and you eat it. It's all possible. These are all potential applications of liquid marbles, okay? So they are important species, but somehow there are many limitations in terms of its fabrication and implementation, okay? So in 2019, we were going through this paper for some other interesting applications. Then we identified this, these are actually the impact dynamics of droplet under different Weber number. Okay, you can see Weber number is actually proportional to the square of the velocity, right? So it actually how fast it comes. It's basically based on the energy concept, okay? So then you can see at very small, the droplet remains same, right? Some deformation always happens, and the velocity vectors you can see, right? The velocity vectors actually, it goes up upon impact, right? Then as you go ahead, and if you goes to 300, the splashing will happen. If you droplet will splash, and from these regions it will detach, right? That means because of the instability, it will detach. That is not useful. But in a specific range around 30, there is a very beautiful thing happening. Okay? If you are very careful, that's what, in science most of the time, the curiosity, observation, because this was known to the people for a very long time, but nobody used it. Okay? And this very beautiful paper inspired us. Okay? You see, I hope everyone can see, right? So this is the situation. A droplet impact and reaches to its maximum spread. Okay? You put a droplet, yesterday I taught you some basic physics, right? Suppose if it is a hydrophobic surface, superhydrophobic surface, what will happen? A droplet you are putting on a superhydrophobic surface, what is going to happen? It will bounce back. It is not useful for me, right? Because the selection of the surface is very important, right? Then you are using a superhydrophilic surface. It will completely spread. It will not come back like that, right? So you need actually a hydrophobic region where you are not in the extreme. It should be the case in our life also, right? Okay? So what happens is upon droplet impact, it spreads. Okay, it's non-slip, slip is fine. Don't need to worry about this blue and green, fine. So if you are careful, you can see you follow the flow field. Okay, you can see the arrows are like this, and on the other side the arrows are like this. That means you have actually a shape like this. We can assume it is as a cylindrical for simplicity. Then there is a point where you have a velocity vectors in the opposite direction. It is something similar to a stagnant region, right? So then our question was, suppose a hypothetical scenario, we add particles. That means, they should form a ring, right? Nobody observed that ring till 2020. That was our first hypothesis. Yes, it should form a ring. Is it useful for us? Science-wise, yes, but practical-wise, I don't know. Because it will be immediately changing, because it's not a stable state, right? Then once this process is over, the surface tension will take over, right? We will discuss about the energy associated with the impact and all in the coming slide. Then the droplet will come back. Then the flow field will change. So whether the ring can collapse, if it collapses, it can make one type of particles on the liquid surface, right? Then can we fill the other side with another particle? That was the hypothesis. I hope that up to this point it's clear. So we designed a surface having wettability around 100, 110, 120. Yeah, 120 based on some condition. And we fix a Weber number of 30 to 35. It's our starting point, okay? The reason is very clear, right? Why we do that, right? So this is the exaggerated version of what actually is happening, what I explained. You can see in the squeezing zone we call. There is a region where particle can stay stably, right? And that's actually very close to maximum spread situation. It is not at maximum spread, we will tell later. And towards the retraction, you can see the velocity vectors are axisymmetrically going towards the crust, right? And the velocity is increasing like anything. That means the particles should go to the crust. This was our hypothesis. So based on that, basically, she made a beautiful the image, graphics. This is what we expect, okay? We have actually a droplet. Before impact, some particles are captured, randomly distributed. You put and you remember that flow field, what happens? It should make a ring. Then, that is not a stable because surface tension will take over. It should retract, right? While retracting, this ring should collapse, right? That collapse should lead to a crust particle deposit, okay? And that is also not a stable situation because immediately these, the capillary waves, the oscillations will happen, particles will disperse again. So can we arrest that? That was the other question, okay? So I hope this hypothesis is clear, right? Yeah, this is the corresponding velocity vectors and all the magnitude. You can see just after the maximum spread, the velocity is getting more and more similar in the opposite direction so that the particles are more stable there. Details, okay? So up to this point, everybody is fine? Okay, still we are not reached to marbles. No, not even liquid marbles, okay? So then we have to test this hypothesis, right? We designed everything. You see, we were amazed. It works right like that. And we have to spend months to get this video. Because we are using some 300 nanometer particles and our surface is black and what's oscillating, that means any type of imaging you try, you cannot see the particles, right? Because it's oscillating. Shadowgraphy you cannot use because it is black. And shadowgraphy is not a good technique because your surface is oscillating, that means it's continuously changing its lens shape. Reflectometry is also not a good way because the surface is oscillating so that whatever the information you are getting may not be actual. We developed optimized the illumination angle and a kind of dark field, right? A long distance dark field. That's where the multidisciplinary approach works well because my background is optics, so we really put effort on this imaging part. And you see the result. As the first time experimental observation upon impact, and many fluid mechanics people also appreciated this one, including Tropia, okay? So we can see whatever we drawn in the previous case, and in this case, I would say the images were drawn first, before the experiment, okay? This is not the reverse, okay? So we had the hypothesis should happen, then we selected the particles, droplet, impact condition, surface wettability, and it works. Now, okay, this is good enough, good for a paper, but not a marblet, right? Then Lakshmi was very creative, okay? What she did is, okay, let us have a projectile motion, okay? So we have actually a bed with a slightly slanted angle and let it roll over a fixed distance, because this we can control this distance. That means the number of particles on the droplet can be controlled. So there is a design criteria over that. And since it is this one, it will come in a projectile manner and go back in that axis, so that it will not go up and down, right? If it goes simply up and down, there is no use, right? So it has to be, ultimately we have to collect it, right? So this angle, 8 degrees, right? So this angle was optimized in such a way that, I should be able to connect. So what is happening here is, okay, he collects white particles, and upon falling, he spreads, right? When he spreads, this all white particles forms a ring, right? Because you have seen the flow field is from bottom as well. That means that's a very interesting situation. You are actually making new interface, right? Because you are actually squeezing, you are depleting particles. That means you are making new interface. Who is really happy to absorb more particles? Okay? And on the bottom, this particle, this surface, we have free particles on the surface. That means wherever new interface is forming, it is coated with the other type of particles. Okay? That means it is a situation, you have actually a ring on the top, visualizing. On the bottom, you have actually new particles being coated, and it will retract. During retraction, that central particle is actually, you have already seen, it will go to the center, right? That means you get a Janus marble, right? Before seeing the actual video, I will show you. But before that video itself, the situation is clear, right? Very simple, right? We got very beautiful papers and patent from this simple idea, and it works amazingly well. And one PhD over, second PhD, she's running behind it, okay? Okay? So these numbers really matters. 5.56 degrees, 10 microliters, 75 mm, everything matters. Let us see the video. Okay? This is my droplet. It will come like this. You remember the setup, right? You have to keep your memory very active. So it comes with some small number of particles. And this is my second particle bed. You have seen that black, right? Let us see what happens. You see it comes. Okay, very nice. You see the depletion. You see the depletion. New interface is forming, right? And on top we will see later. You see, while it goes back, you see he came as white one, right? While it goes back, you see, it's beautiful oscillatory behavior and all part of the energy dissipation. You see, now it is a Janus liquid marble, right? And he will stabilize later, because since he is having still energy, he will want to dissipate it by oscillation and all. You see, all this triangular, all these shapes are part of the impact dynamics. You got a Janus liquid marble in 20 milliseconds. 20 milliseconds, 30 milliseconds, right? And here it is highly reproducible, because we use a very basic physics to do that. If you do manipulate too much the nature, repeatability will be a problem. Here, the problem I can tell you, because it's not like the best method which solved all the problems about Janus liquid marble, no. Because this oscillatory behavior is a problem, so that the number of particles, first particle, second particle ratio will be the same, but the boundary will not be sharp, because it's part of the physics, because you have to compromise something, right? So if you are not worried about the shape, beauty of the structure, but more on the matter side, this is the one you can use. I hope it is clear up to this point, right? I hope in a simple terms I explained. And this video was like, one of the landmark for our lab's growth, which attracted many professors, which helped us. Okay, fine. So these are all details, and you can see Janus liquid marbles produced. I already warned that he will not make identical boundaries. We want to show that in the paper. but the number of particles are within the error bar. I don't know whether its numbers are here or not. It's not there, but within the error bar or something like 4%, which is completely acceptable. Okay. So then, just to give you an idea, what is exactly happening, a droplet before impact, it comes with it's fixed at a particular height, so it's associated with the potential energy, right? And we are releasing the energy associated with that and the surface energy because of the surface tension. Okay, and once it falls on that, it will spread, right? That is one way of releasing. The other one is it can make some craters, right? It can, if it is a deformable or powdery bed, some energy will be lost, right? And then the viscous dissipative is also happening, and a significant portion, like 40%, half rule is there, right? 40 to 50% is given for making flows. That means our approach is highly effective, right? Because we are using flows. Got the point? And we did some simulation, theoretical, experimental, you see? Acceptable range, very good in shape. Okay, and theoretical stuff, we'd have a Langmuir with a group in Professor Samir Dalvi in IIT Gandhinagar. Okay, so this one we will not touch it. I will just give you some idea. Okay, so then like the liquid marbles, conventional application, you can use magnets to transport and all. Some fancy things you can always do it in the paper. Okay, so now you find a way to make Janus liquid marbles without putting much effort, high reproducible and fast. Okay, yes, polarity particles, in these experiments we use dummy particles. Such things like the charge of the particles, that kind of details we haven't explored yet. Because that definitely matters when they do self-assembly. Here basically it's all more of a forced assembly. Because droplet, the impact is something like if you translate it to time, this effect is happening in 0.1 millisecond, 0.2 millisecond, and it spreads over 4 mm, 5 mm in diameter. You convert that into velocity. Okay, the other properties, I'm not saying they are insignificant, but heat will be dominating. Okay, but if you give time and ask them to orient themselves to make a marble, definitely polarity will be matter. Here we are not giving such flexibility. Even these marbles you are seeing, one is 300 nanometer, other one is 20 micrometer, right? So such a huge change in particle size also is possible because they don't have any freedom to choose. They have to follow. Okay. So then the point is, okay, this is fine. Whatever we achieved is very good, but it's not good enough because typically you can make these drops and all for 4 microliter, 10 microliter, 20 microliter, but the real beauty happens in the sub-microliter regime. And making Janus liquid marble at the sub-microliter regime was very, very tough, and nobody have done it because you have to split, right? That means if you want to make a 0.5 Janus liquid marble, 0.5 microliter Janus liquid marble using conventional approaches, you have to make a 0.25 Janus liquid marble first, right? And you have to collapse, right? That is really, really tough. Got the point? So then we thought, okay, can we extend this approach to address that challenge as well? So we did some adjustments in our setup. The same setup exists, but some minor adjustments. I told you. Yeah, the status quo at that time was like, people were able to make Janus liquid marble even without our method, because in the first paper what we showed is like a 4 microliter. 4 microliter, other people also achieved that. So approach-wise significance is there, but the impact-wise, the question. So can you break, some sort of barrier existing? That was the question. Can we make Janus liquid marble less than 1 microliter? It's a very good question. We thought, let us try that. Okay. So what we do is, okay, instead of that Weber number 35, you remember these numbers, because 3 works I will present, I will keep on increasing, okay? Instead of 35, I am using 55 here. It's not a random selection after a lot of thought process. Then in this situation, in this Langmuir, you can see this work. Compared to the previous work, in the previous work you have seen, before this happened, this pinch off happens, the droplet retract and go, right? Here we are not allowing that. Okay? We are actually, what we are going to do is, the whole process, but the energy is significantly more because we are closely doubling the Weber number, right? That means all the particles, the white particles reaches here, right? It's actually pushed out, not in the form of particles, but in the form of droplet. That means this baby droplet will be carrying some sort of particles, only one type of particles. Can we use this guy to make Janus liquid? That means from a parent droplet, if it works, from a parent droplet you will get 2 babies. One baby will be good, fat enough. The other baby will be very small. It's very good, right? In a same setup, And then you have a lot of freedom. What kind of particles you can put it on the other side. You can make Janus, pristine, all control. So that was the thought process. I hope everyone is in the same boat. Yeah, we do simulations to see. Because these simulations are very important, This gives us these numbers. Very important. And you can see, like, if you follow the flow field, a very strong flow field towards the top. And because of, the instability happens at the neck, it will break. And what will happen to this drop and what will happen to this drop is the question. Okay? So this is our improvised setup. I hope you are able to follow previous figures in your mind. So what we do is, now we have 2 impact. Okay? Same starting phase. All these, you may be checking, okay, previously it was 70 mm, now 80 mm. I told you there is a particle collection criteria, right? It goes in an inclined manner so that, we will have impact also in that manner. So this guy goes, and here we put identical particle. You remember previously I put black one. Here we put identical. You can put a black also, depending on what you want. Okay? So then what happens is, you remember what is all happening in the droplet, right? Droplet, and it will pinch off and it will carry a small number of particles, right? And he is allowed to fly and go and impact in the particle number 3, particle bed number 3. Following or not? The droplet is coming, babies are produced, small baby can fly far, right? He will reach here, we can estimate this, we placed the other particle bed there, and this is too fat, he cannot fly much, he will be falling somewhere here, right? Either you can collect it like this or depending. Okay, and here I am making another Janus liquid marble because he is also doing the impact, right? So I can adjust the height of this one to have the required Weber number. This cascade system, you understand? Okay? But once you set this one, you don't need to do anything. You just put a droplet. Okay? You will be having 2 marbles. It can be Janus, it can be pristine, I will show you. Now this is what is happening, okay? A white droplet is coming, okay? And you can see a baby is jumping out, right? And another baby went in that direction, right? Because, it's in an angle, so you will not see it in the same axis. This is what is exactly happening for 10 microliter droplet. You can see the starting of the jetting, right? Let us see that in the side view imaging. Yeah, this is what is happening, okay? So 2 types of, you remember we have the particle bed 1, particle bed 2, particle bed 3, right? We change particle bed 2 to, one is white, the other one is black. This is corresponding to white, and this corresponds to black. Okay? You can see that the PLD, what is the particle laden droplet, it forms and hits there. You see all this impact and beautiful pinch of what we designed. You see, it actually forms as a Janus, it forms as a liquid marble, pristine liquid marble, beautiful liquid marble. But in the second case, it is actually black particle, so you get a Janus liquid marble. And what happens to this baby? Because we haven't considered this baby in this figure 8, right? What is this one is the one happening from the, and there will be still larger ones, microliter. They are not meeting our purpose. Okay? So, do we have videos for that? Yes, you can see. Beautiful videos. So, you can see white first particle, second particle bed, white particle laden droplet, coming, depletion, all the physics you have seen previously is happening again. Only thing is more rigorous because we give more energy. Okay? You can see a partially coated, right? You can see the depletion, right? It is not completely coated. And he is actually pristine liquid marble. And he is actually Janus liquid marble. They are big. Let us see what happens to the other one. That boundary is not so bad, right? It's good. Okay? We did a lot of characterization to see, okay, we can go up to 0.1 microliter. So you can read the papers. Yeah, a lot of characterization to say that physics remains the same for different range of volumes. You see some normalization, beta, spreading parameter, some other normalized numbers to convince you that, okay, it works. Okay? So, yeah, all these things are not so important at this point. Yeah, then what happens for the babies? So, the small baby you have seen is still continuing its flying, right? Yes or no? And he will be falling in on another particle bed, right? You see, pristine marbles are formed, right? If you place the identical particles there. And if you change the third particle, you see the beautiful sister and brother kind of approach. Because, we used 3 different kind of particle. One is white, the other one is black, the other one is pink. The larger one will be black and white. The last one will be pink and white. Black is not being transferred to the third one. You see the beauty, right? It's not a mixed marble. You perfectly design what is our outbound. Because only the white particle will go towards the top, and that is where we cut. The white particle cannot reach there. Before that, the process is over. So the first one will be black and white. Yeah, this is the corresponding setup. Black and white. Okay, this is what you see. And you have seen a lot of videos, so you have to trust it works. Okay. And this guy jumps and goes there. Baby is formed. You can see. And their shape is much better. Boundary is much better, right? Because they will settle much faster, you see. The larger one will have a lot of oscillatory behaviors and all. Good? We did a good job till now. Because, we made the Janus liquid marbles of 100 nanometer, 200 nanoliter, which was not possible with the conventional approach. Okay, good. Then, because, the stability of the marble is super important, right? Because, whether it is mechanically stable or not is the question. We make and beautiful images published, fine. But whether it is only the images or you can actually really work with that is the question, right? Because in most of the marbles, we have to put it on water surface, solid surface, transport, apply magnetic field, electric field. So you see the beautiful result. This is our conventional marbles till the before our, our approach. And these are the marbles we produced. And we measured the mechanical stability by pressing and measuring the critical pressure. We apply, using a weighing balance, we push and measure the area with which it breaks, which will give you the critical pressure which it can withstand. It's one standard way of understanding the stability of marbles. And you see, the babies we formed are super stable, right? Compared to the larger ones, right? Agree or not? That is impressive, right? Because he's much, the smaller ones are much stable. Okay, we have some answers, and I ask you, because all of you are researchers, why it is so? Keep that question in your mind. Okay, we have some hypotheses, right? It could be small, less defects, they have more packing, more sphericity, that also matters. But if there is any other reason, we don't know. So I leave that question to you. Okay? But the point is, if you want to transport it, you want to put, you take a beaker and you put a number of marbles you want to carry as medicine. The mechanical stability is super important, right? Because it should be able to withstand the pressure of the other marbles also, right? This graph says these larger marbles will collapse very fast, right? And the problem with the marble is if one marble collapses, that liquid can actually go to the other marbles and make problems. So you need a very good stability. So this graph tells you that, you use our method to make better marbles which have better stability. That's good. Now, okay, what about its, because I told you he can sense the environment, right? We do very simple reaction. If you have any doubt about the reaction and how it works, you can ask Ardra. I'm not an expert in that. It's phenolphthalein ammonia experiment, right? So you see it will change the color. Okay, this is one of the important application of marbles because, it can act as a sensor. Okay, it can act as a sensor. You see, it's not in a very controlled environment, but still it's a decent experiment. You see, this guy changes color much faster, right? The babies, right? Because of the surface area contact and all that, because the comparing to the volume surface area relation. So it is always better. The previous two slides tells you that it is always better to work with the small marbles, right? Because he responds much faster. He is more stable. So these two information, first we have to produce, right? That is actually the importance of our work. We are not saying this approach is the universal approach from now onwards, no. But it actually tells you that, okay, this is the way we have to think about. And the whole work complete in 50 milliseconds. In 50 milliseconds, the process is over. Then you can put the other droplet sequentially. If you make a rotating setup kind of thing, sequentially, continuously, you can keep on cooking marbles. Okay, so I think in last 5 minutes I will stop. Okay, I hope till now everything is fine, right? Any doubt till now? Because now we are moving from marbles to something other important applications. Yeah. These are PVDF or polystyrene, right? PVDF, right? PVDF for polystyrene having contact angle or hydrophobic. That is, phenolphthalein is inside, right? Phenolphthalein is inside. The core liquid is with phenolphthalein. Yes. It's a porous, right? Yeah. That is actually one of the importance of liquid marble. Actually, you can control the reaction with the environment. Okay, and it responds much faster than its larger. Yes. Yeah. Yes. True. Oh, evaporation is a problem because they are still porous. So typical lifetime is 30 minutes, 50 minutes, right? Depending on the volume. And physics-wise, you have limited ways to kill the evaporation, right? Because it is porous. And you have to sense. Means, you have to compromise something, right? Yeah. So then I will not tell more further because you wait 2-3 months so that you get a new paper which solves partially this problem. Okay, we are working on that. Very good question. Okay. So let's go to the next. Can we reuse this water? Important question, right? If you use water for cleaning and it get damaged or it get waste, it's not a good sustainable model, right? Can we reuse it? That means can you extract the particles out? That's a very important or challenging problem in microfluidics because it is not that easy. Because either you have to apply electric field, magnetic field, it should be stimuli responsive. But in dust, we know what field we have to apply. So we thought, okay, ours is flow. Like, your question was whether polarity, charge, effects. So ours is not based on such properties, based on flows. So can we use this one, using flows? Okay, this was the question. That means from a capture point of view to extraction point of view. And this is very important for, whoever works with the microfluidics, we need a very small droplet, right? That is our first aim, right? With the maximum number of particles. And it is called the enrichment, right? For many reactions, we do enrichment or, evaporation to enhance the number of particles, right? Then only then, if you take a microscope, you take a droplet having 100 particles, some number I am saying. The chance of detecting that 100 particle from that big droplet is very, very, very small, right? Or the sensitivity of your measurement will be having very less, right? Suppose the same number of particles you can give it in 0.5 microliter. That means all the particles are in a very small area, right? Small volume, right? That means the signal comes out from that will be very high, right? That's called enrichment. Typically, people use electric field, magnetic field in channels, not in free droplet surfaces. So we thought, okay, let us try that here. And we got published, our work got published in Physics of Fluids, very nice. So what Lakshmi did is, okay, these are introductory, I am skipping, I already told. Challenges and all I told. Lakshmi, what she did is, you remember that Weber number 35, 55. Now you can see 65. Okay? Images look same, but here the difference is the bottom particles are completely free. Bottom surface is completely free from particles. It's like a solid surface. Got the point? So there is no capturing of particles happening at the spreading phase. So whatever the dust particles or your target particle, depending on your application, it has to follow through these processes. And this 55 to 65, we did it on purpose to ensure that maximum number of particles reaches there to take it out. Now you think about this droplet and this droplet. This droplet have significantly larger number of particles, right? And this is a depleted one. This is an enriched one. Okay? Schematically, it looks nice. Let us see whether it is working like that in practice. All flow field simulation. This is the setup. You can see, 0.5x, 1x, 2x, all these things are number of rotations to check how many particles are being coated to check the efficiency, okay? Efficiency of extraction. And it's a hydrophobic substrate. All these things are, I think you can understand now. And the angle of inclination now changed to 12 now, right? From that 8, 6 in the previous works, right? All based on some logic. And Weber number is fixed around 68, 65. So let us see a video. I think I will stop with this video. There are a lot of characterizations coming, but you see? You see the difference between the large and the small? Ardra, can you play that video one more time? We colored that droplet to have a better impact. And the baby will come down very soon. Yeah. Yeah, play that one more time. A droplet with some adsorbed particles is about to fall. Very simple experiments. Very simple experiment. You don't need any electric field, you don't need any magnetic field, nothing. You just need to put it at a 6 centimeter height. You can apply this in a remote environment, in a lab on a chip device where you have to, the measure, where your boss is working, remote area. This is very good way for enrichment. We have to test it for biological material because they are. I will discuss that with the Damien. That is the next phase we are thinking. Yeah, it's working. Slideshow, you go out and come back. Yeah. Okay, so they will make the video working. We have to finish it in 2-3 minutes lunch time. Okay. Anyone can guess on the efficiency? Efficiency means suppose 100 particles are there in the parent droplet. In that tiny baby droplet is our target, right? How many particles will be there? 100 is there coming. 100 particles are coming with the droplet. Can you give a guess after seeing that video? Question is clear, right? How much will be going to that baby droplet? That is my target now, right? 75 to 80. 1:10 means 90 will go to the baby. Okay. Any other numbers? These are all optimistic numbers. Any other numbers? Even 20% is good, right? Anything above that initial value is always good for me. So that was my target, okay? At least double. Then that claim is good, right? Double. Okay, let us see. Yeah, move the slides to next. Okay, all this characterization we did. This is the result. You can cross 90 as well. Okay? And depending on number of particles, because you are actually cutting the neck, right? So where you cut the neck will have, if the particles actually all goes here, if you cut 100% efficiency. If the particles are here and you cut here, 60%. That is what initially I told, number of rotations, right? 1x, 0.5x, this characterization tells you, on x-axis, that's what you see. These are all for 300 nanometer particles, 300 nanometer particles. Because we have to see whether it works for other type of particles, right? We did this experiment with the 20 micrometer particle, which is really far from the initial particle size, right? You see the efficiency is even better. It's increasing because, they can follow the flow field even better, right? Stokes flow. Only condition is, in this work, we restricted ourselves on hydrophobicity because surface particles. But our assumption is, or our initial thing is, even the dispersed particles we can enrich. That's an ongoing work at the moment because you have to do some sort of adjustment in the system. So what I want to say is, without applying an external field, then people can say you are putting the droplet from a height. Okay, something you have to do to get something, right? And we are not adding any surfactant, no electric field, no magnetic field. So it's more sustainable, right? Because you are not disturbing the system as it is, right? Because then when you think about a biological application, you want that pristine system to be worked, right? You want to preserve it, right? But if you want to apply a field, because these are all charged molecules, right, in biological systems. So electric field can have some sort of secondary effects which we don't want. And the proof of principle stage, it works very well. And we got funding from Kerala State, the ministry, for this work. And we did characterization. You can see the same numbers comes in 2 independent approaches. Instead of 90, we are getting 88. Instead of 64, we are getting 61. Is perfectly okay. That's all from my side for today. So yesterday we have seen how the droplets, right? Today we have seen a bit of solidification of the droplets, liquid marbles, and a bit of, another important challenge of microfluidics is basically, or soft matter, I would say, is the extraction or enrichment. So you see a potential of that as well. Okay, this is completely my previous PhD student's work. Dr. Lakshmi, she is actually in an inkjet printing company as a scientist now in UK. So this work is important, right? Yeah. Okay, with that I stop for the talk.